Alright, we are live. So, how is everyone?
Doing alright, Nick. How are you doing?
Doing alright too. Thank you. Alright, how'd PA2 work out? Yay, Friday, definitely. Hey, if you can match the test output, you are probably good to go. Awesome. So any reflections or takeaways from PA2 as far as you know, moving deeper into objects and object-oriented programming? Objects are objectively important for object-oriented programming. That is deep. Alright, object haikus cannot be far behind. Not a related question. Yeah, you can use interrogation in Java. Same thing as in C. You know, something equals condition interrogate A:B. And if the condition is true, this is equal to A. If it's false, it's equal to B. That still works. Typically for an assignment or a print statement or something like that. Concatenation. I feel like Java tried not to break anything that worked well in C. Alright, so yeah, objects are definitely nice, right? They do make our life easier. Once you know which ones are available, which classes are available, and how to use them, we can just make these objects and do a lot of heavy processing with without having to do too much work ourselves as far as implementing code. Ended up using regex in PA2, so you use that to pick out letters, I assume? Cool. Regular expressions are nice in Java, and if you embrace regular expressions in 224, right, you can do a lot of pre-processing of text. If you wanted to, you know, throw away spaces or throw away certain characters or convert case or replace one thing with another thing, right? If you put that in the language of regular expressions, there's a whole, you know, set of classes around compiling and using regular expressions in Java. There's a lot in Java, and most of it we're not going to get through, unfortunately. But pretty much anything you can think of, you're probably going to be able to find classes and packages for in Java. I think you could probably run Valgrind when you say Java, but it's never going to give you the information you want. I mean, it would tell you if the JVM had memory leaks, which, you know, would be kind of cool to discover if it does. But Valgrind we mainly use to find memory leaks and executables, and if we had a Valgrind inside the Java environment, it wouldn't really make sense because we have this garbage collector running around. But I think you can interrogate the garbage collector and get some information that might be useful. I don't actually remember how to do that. Oh, that's a whole tutorial. Don't want to do that. Might be part of the runtime. Yeah, dig into that if you want. Black Ops integration methods, cool. All right, so yeah, hopefully objects are making some sense and they're feeling like more of an appropriate way to do these things as opposed to, oh great, I'm in 223, I gotta do objects, I guess, because that's what we do. All right, so hopefully it's continuing to make more sense. Cool, nice. I think I need my glasses. There we go. Good, good. Yeah, that was the intended goal, is that it really kind of gives you an opportunity to totally work with this idea of objects and classes, and kind of, you know, any other approach is going to be so much more difficult, that it really kind of compels you to dig in. And yeah, it was a step up. Did you find your code was shorter than you might have expected when you first read the assignment, though? Which is kind of fun. It's a cool discovery to make. And I mentioned that mine was like, you know, 80 lines, and it was actually 40 lines of real code. And I already saw some submissions that do better than that had, you know, maybe 20 or 30 lines of Java, which is kind of cool. All right, you know, you can run your indexer on we had the text for Wuthering Heights in our 224 class. You can go ahead and run it on that and have all kinds of fun. And it's pretty efficient. Ooh, that's not what I wanted. So let's just run this on War and Peace. So War and Peace is 63,000 lines of text, 500,000 words, and our indexer pretty fast. So let's just capture the output. So I mean that's you know, not bad speed. It's a whole lot faster than doing this in Bash probably. But yeah. So is appears a lot of places. Parallelogram appears in War and Peace? I don't think so. Yeah, how many times does War appear? My VI is kind of dragging on this file. Oh, because this is all one line. Yeah, a fair number of times. All right. So let me know if you had any lingering issues with PA2. We'll I'll get it graded this weekend. I'll give you some feedback if there were any issues I saw. But if you know, same as I always say, if you weren't quite sure what was going on, right? Even if you got a good grade on it, if you're not quite comfortable with what you were doing, right? Definitely come by and talk during office hours or ask questions here. Because PA3, we're going to shift gears. We're going to go back to more of a 222 style assignment where we're creating a class from the ground up. But then in PAs 4 and 5, we're really just going to start using classes again and putting pieces together. And PA 5 in particular is going to be a lot of using classes and digging into the methods that are available and putting them together in the right way. So it's going to be a much more intense version of PA2. So if PA2 felt, you know, kind of cool and fun, that's great. You'll be in really good shape. If you're kind of iffy on it, let's definitely go over what you might be struggling with or unsure about, and that'll get us set for future assignments. So yeah, let's talk about PA3. So PA3 is posted, and I gave you 2 weeks for PA3. I'm not sure why I did that, but that's what I originally set up in Canvas. And I think that was just to kind of give a bit of a breather because we've been going, you know, 1 week per assignment. So PA3. Yeah, we should do like a networked graphical version of the stick game. We could do that. Total of five large programming assignments. So the fourth one will be GUI based. The fifth one will be networks, and probably it'll be a networked version of whatever game we do for the fourth one. Wonder if we could make like a really cool like first-person stick game or something. All right, so PA3. Let me pull up. Make my window persistent. Let me just pull up the assignment and let's start talking about this. So this is the famous 20 questions game. So how many people here have played 20 questions? Cool. Awesome. So yeah, 20 questions, you know, you have two people, one person thinks of something, maybe they're thinking of an animal or, you know, a thing or something like that. And the other person gets to ask yes/no questions. And you can only ask yes/no questions, and the person answers honestly, you know, yes or no to each question, and you try to guess what it is that they're thinking of. And yeah, they sell or used to sell these little toys you could get that, you know, it would have a little display and it would say, you know, are you thinking of an animal? And you'd say yes or no. Does it have fur? And you'd say yes or no. And within 20 questions, it would almost always be able to figure out what you were thinking of, which was really kind of freaky, right? Yes, it was a cat. Wow, you're good at this. And so we're going to code this in Java, okay? And it's going to use basically the same approach that these little toys use. The same approach that people who are really good at this basically use. And so we're going to be implementing something called a decision tree. And the information about, what you should guess is going to be stored in this this tree-like structure. So here's the basic setup. Imagine a tree where each node is a question. So is it an animal? So that's going to be a question that you ask the person first before anything else. And if they say yes or no, that's going to affect what our next question is. So if they say yes, we're going to say, okay, I think I know what you're thinking of. Is it a cat? And if they say no, it's not an animal, we're going to say, okay, I know what you're thinking of. You're thinking of a laptop. Okay, this is not a very good decision tree. But, we might get lucky. If the person is into cats and laptops, we'll probably be able to guess what they're thinking of. But we could make this better. Instead of saying, if it's an animal, it's a cat, we could say, here's another question. Is it furry? And if it is, then we'll say, okay, I think it's a cat. And if it's not furry, we'll say, okay, I think it's a turtle. And over here, if it's not an animal, instead of just jumping to the conclusion it's a laptop, we could ask another question. Is it electric? And if it is, then we'll say, okay, I think it's a laptop. And if it's not, then we'll say, okay, I think it's a rock. So now we have 4 possible answers based on a total of 1, 2, or 1, 2 questions. You could consider humans animals in this case. And rocks are just unplugged laptops, no, or bricks maybe. So this is a really simple idea, right? But it's really powerful. So each time that you ask a question, you move down one level in a binary tree, right? So with one level, we had 2 possible answers. By adding one more level and having 2 levels, we have 4 possible answers. So if you have a total of 20 questions, how many different answers can you have? How many different things could you identify? Definitely a lot. 2 to the 20th. Yeah, it's not quite 20 factorial, but 2 to the 20th. Which is the number of leaf nodes in a tree with, 20 steps from root to a leaf node. And so 2 to the 20th, how big is that? Ballpark number. It's a pretty good ballpark. Yeah, so approximately 1,000,000. So rule of thumb, 2 to the 10th is 1,000, 20th is 1,000,000, 30th is 1,000,000,000, 40th is 1,000,000,000,000. So 1,000,000 different things that we could discriminate between by asking 20 questions. That's why that little toy that you get seems like it does such a freaky good job of figuring out what you're thinking of. Because if you can differentiate among 1,000,000 different things, most people don't know more than 1,000,000 animals, right? So by putting in the right set of questions in this decision tree, you can make something that looks like it's smart, right? It understands different types of animals. Now, arguably, it's not actually smart. It's not actually intelligence, right? It's very programmed. But, it's a pretty impressive behavior. So, let's see what we got here. So there's a really simple Q&A file. Okay. Is it an animal? And if it is, it's going to be a pig. If not, it's going to be a rock. All right. So that's a simple starting file. A more complex one, and this is available on the server, is this one. This is 40,000 lines, so about 20,000 questions or answers. This came from a former student who was at UW, and they had an assignment similar to this, and they were given this file, and I think you can find this online. But this is a pretty extensive database. I believe it's crowdsourced, so there's some stuff in here that may not be quite right. And it's also, you know, subjective when you ask, is this a large animal? Some people may think, you know, that a cow is large. Some people may think it's not. So this is not a perfect database. There's a lot of noise in here, but it does a pretty good job. So let's see if I have a I'm going to pull this over here. All right, I think this will work. All right, so who wants to think of an animal? And this only works on animals. All right, go for it. All right. So so think of an animal. Don't tell us what it is. So so this is Nathan. So can it fly? Yes. Does it have feathers? No. Is it extinct? No. Does it eat nuts? No. I hope I don't have to actually say N-O. Does it hang upside down? Yes. Does it suck blood? Yes. Is it really, really big? Does it hibernate? Yes. Again, does it suck blood? Does it talk? Is it a vampire bat? Just a bat, but yes. Cool. All right. So we can say yes. There you go. Thanks for playing. All right. So you know, we're not requiring that you take 20 questions, and we're actually not cutting you off at 20 questions. But the goal here is to develop the code that will play this game. So here's the other thing. Let's play it with our simple database. It asked the same question twice, probably just because of the way that people had answered questions in the past. It's a fairly randomly built database. So let's play this with our simple database. All right. So thinking of an object. Okay. So somebody else think of an object. First person to chime in. Who wants to think of an object, but not tell us what it is? Okay. All right, Thomas, go for it. But think of a different object. All right. Is it an animal? No, I guarantee it's not. Well, unless you're being alternative. Okay, so it's not an animal. All right. Is it a rock? No. Okay, so you have defeated the mighty 20 questions game. All right. So now it says, what were you thinking of? A picture frame. All right. So please tell a question for which yes means a picture frame and no means a rock. So I don't know, something like, is it square or do you hang it on your wall? So I don't know if you're typing in an answer to that. Do you insert pictures inside? Okay. All right. Thanks. I'll try to do better next time. All right. So let's play this again. Is it an animal? No. Do you insert pictures inside? Yes. I've got it. Is it a picture frame? Yep. All right. Is it an animal? No. Do you insert pictures inside? No. I've got it. Is it a rock? So it's gotten smarter in some sense, right? It can differentiate between a rock and a picture frame now. A cow is a large beast. Okay, cool. So yeah, so what just happened is this 20 question file that we started with, which had 6 lines, now has an additional pair of lines, right? So if it's an animal, yes, it's going to say a pig. If it's not, it's going to come down to a new question and say, do you insert pictures inside? So this database will grow the more you play the game. And so that big question database, I think, was crowdsourced. I think somebody put this on the web and let people just play it, and it gathered up their answers. All right, so Peter has something. So, all right. So let's play this. All right, is it an animal? Yes. Is it a pig? No. All right, what were you thinking of? Nick. Okay, what's a question for which yes means Nick and no means a pig? Hopefully that's not too hard to come up with. All right, you're assuming pigs aren't good at teaching CS. Yes, it's a Nick. All right, cool. So you got the idea? And this is yeah, can make pizza, but maybe pigs can too. So this is a fun program. Once you start getting it to work, it's actually a lot of fun to play with, and it's fun to like show to your friends and have them mess around with it and see what kind of database you come up with. Right, so now, you know, our database file has gotten bigger. All right, so that's the basic effect of this game. So how are you going to implement this? There's some high level details in here, but we're going to talk about this a lot in class. It's not all written in here. In fact, most of it's not written in here. So this one you're definitely going to need to, you know, take notes in class or go back and watch lectures or something like that. And it's going to be more coding than what you did in PA2. But again, if you work through it methodically, it's not a bad assignment. Let me see. So looks like my code was about 200 lines of Java. Yeah, 200 lines. That's good. And the real guts of it was less than 100. So, but I mean that's kind of an arbitrary measure, right? But just to give you an idea, it should not be, you know, thousands of lines of code. It's a really simple algorithm to implement. Okay. There's basically a few pieces. You need to read in the database file to begin with, and then you need to play the game, and then you need to update the database if the game got stumped at the end. Okay, so three steps: ingest, process, and then update, which is, you know, most programs in the world: input, process, output. Um, so submission details, right? Make a subdirectory in your repo called PA3 and make your main program pa3.java. And I'll compile it by typing javac pa3.java. If anything else is required, give me a makefile. Same drill as usual. Okay. High-level details. So you're going to implement a binary tree. Each node has two children, which we're going to call yes and no. Yes will be on the left, no will be on the right. That's important. Would you be mad if we got the lines of code down to 1? Yeah, so that would be a good challenge. But you'll comment it, so your comment will be 1,000 lines, but your code 1. That would be righteous. All right. So you're going to implement the binary tree. To play the game, you basically begin at the root of the tree, and the root's always going to be a question. So you're really just traversing the tree. You start off at the root, and it's a question, and so you ask that question: is it an animal? And you get an answer from the user. And if they say yes, then you move to the left subtree. If they say no, you move to the right subtree, and you ask that question. And whatever they say, you move to that subtree and you ask that question. You keep going until you get to a leaf node. And when you're at a leaf node, you've got what you think is your answer. And so instead of asking a question, you say, I've got the answer. I think it's a turtle or a laptop or whatever. Can we ingest a blank database? So you can assume the database has some information in it. And the smallest non-blank database is going to be 6 lines, a question and 2 answers. And we're not going to worry about, you know, corrupt databases or things like that. We're going to assume that you're working with a valid database, and as long as you don't corrupt it, you can assume it stays valid. All right, so playing the game, begin at the root. It's guaranteed to be a question. Ask the question based on their answer, yes or no. Go either left or right, and repeat. Okay, you can do it recursively, but I don't recommend it. I recommend just iterating down, right? So kind of like, you know, when you're searching for something in a tree until you get to a leaf node. When you reach an answer, tell the person what the answer is and ask them if you were correct or not. If the answer is correct, you don't have to do anything. But if the answer is incorrect, then you need to get a new question that helps you discriminate that answer you gave from what they were actually thinking of, and you basically change that answer node into a tiny little tree with the correct answer and the incorrect answer. So the answers are only on the leaf nodes. Every other node is a question. And you're going to start off by reading a database file, and then you're going to build it up. So let me grab a pencil. So let's see how this plays out. So, you know, is it an animal? And I'm always going to put yes to the left and no to the right, so I'm not going to keep writing yes and no. So is it an animal? If it is, it's a cat. If it's not, it's a rock. All right, so you play the game. Is it an animal? No. I think it's a rock, okay? The answer is, you know, no, it was not a rock. Okay, so you ask the user for a question. So you ask them what they were thinking of. They were thinking of a phone. And so you say, give me a question where yes is a phone and no is a rock. And they say, you know, is it rechargeable? All right, so here was our previous question. What we do is we make a new little mini tree where phone is the yes answer and rock is the no answer. And the question is it rechargeable? and we replace this answer node with this new subtree. So is an animal? No. Is it rechargeable? No, it's a rock. Yes, it's a phone. So really, all you have to do is as you're playing the game, move down. When you get to an answer, if the answer is incorrect, get this information from the user, right? What it was. This is what you thought it was. Here's the question that differentiates those. Put those together in a little tree, and change this answer node to be instead that subtree. So how do we do that? Well, you have to know what node you came from, and in this case, change its no child to be this node right here. So how do you do this in practice? Right, you wander down your tree, and you get down to here, and your answer is incorrect. You need to know the node that you came from. So as you're going through, remember the previous node, and you need to remember which way you just went. So remember, this is the previous node, and you just went along the no direction. You gave the answer, it was wrong. Get the new question. Get the correct answer, the answer that was incorrect, and change this thing's no child to be that new question. And now you've extended your tree. Alright, so if the answer is wrong, ask for a new question to discriminate. Make a new node from that question. Those two answers inserted in place of the incorrect answer. Alright, so the initial decision tree is read from a file. Default is 20q.txt, but you can put a command line argument with the file name on it. And anytime that you update the database in memory, anytime you update the tree, you want to rewrite that database file. Okay, so there's our sample 6 input file, 6 line file, 1 question, 2 answers. All right, so last details, and then we'll dig into a deeper level of this. So approach this in pieces, right? Start off with just a binary tree class, which we did a few days ago, and that code is still on Canvas. But it's going to be a decision tree, so you might call your node left child yes and right child no, right? So you don't have to remember those. And you need to know if the data is a question or an answer. And you can do that by seeing if the children are null or not, but you can also set a flag to say, is this a question or an answer? And then, hardwire a tree. Just go ahead and write some statements to set up a few nodes and set the left and right children, the yes and no branches, accordingly, to make yourself a little decision tree, and then just play the game. Right? Just run through and ask the question and keep moving down left or right until you get to a leaf. Forget about updating, forget about ingesting, right? This gets you the basic tree structure, which you have to create yourself. Okay, so you've got to create the decision tree on your own. And it's not a binary search tree, by the way, because there's no comparison of values to the node. But it is a binary tree, and that you're making from scratch. But this part will let you, create the tree class and the node class and write some code to traverse and so on and so forth. And it lets you play the game with, whatever tree you cobble together. And then work on the file I/O, right? Work on ingesting the file. And ingesting the file is pretty straightforward if you do it the way that we're going to describe, which is recursive. And then once that's set, then you can work on the part that updates the tree at the end of the game. But once you can ingest a file and play the game, now you can go after the 20Q big database, and you can explore this with a pretty large database of information. So you can use primitives, scanner, print writer, and so on. Create your own tree class, your own file parser, and so on. Keep this on the command line also. We'll switch to Eclipse for PA4. And we'll start moving towards Eclipse next week, probably. There is no binary tree. Oh, it's on Canvas. Look under the public shared area. And actually, let's just bring that up. So under 223, tree 1. So there's some code. And this is a binary search tree of integers that we coded. That's not what we're doing here, but as kind of a starting point for some of the ideas, it's not a bad point of reference. All right, so there's a pair of test files on the Linux server that you can mess with. And grading, again, pretty straightforward. So if I can compile your code, you get 20 points. That's always good. If it actually asks questions and makes a guess at the end, that gets you another 10 points. If it actually follows what's in the database file, right, so it's actually legitimately reading questions and answers from the file and playing according to that, then you get another 30 points. So now you're up to 60. If I can pick up a different database file with a command line argument, that's another 10 points. And if the update works correctly at the end, that's 15, and the last 15 points are just style points. All right, so implementation is called PA3. You can run it with either Java PA3 or Java PA3 file name, and that should be a database file. So any questions at that level before we start digging down into more detail? It's really not too bad to implement. So I do recommend, making a tree class for the decision tree, making a node class for the nodes of the decision tree, and making a main class to play the game, and calling things appropriately. So I split this into 3 different main classes, and then whatever methods you need in each of those. But see what organization makes sense to you. All right, so let's go into some details. So your database file looks like this. It's a keyword and A, followed by the question or answer. And then if it's a question, it's followed by the yes answer. Yes, it's a cat. Or no, it's a rock. All right. So for our initial file, which looks like this, pretty straightforward to read. Here's a question. Here's the yes answer. Here's the no answer. But really, don't try to make sense out of this file. Okay? Simple case, 3 nodes in the tree, we can do that. But when this starts getting larger, it's really hard for you and I to look at this file and understand what goes with what. And we never have to do that, and you don't want to do that. Okay? So this is really, really important. don't try to make sense of the database file. And if you're trying to patch up, you know, the database with a new question to help resolve two objects at the end of the game, don't start going through the file and trying to figure out where the question was and where the answer is and how to change that. That's a real nightmare. Okay. So instead, we're going to see a really straightforward way to do this, which is to patch up the binary tree in memory and then write it out to the file. Okay, and writing this out to the file is simple. We simply traverse in node left-right order. And then reading it from the file is a recursive procedure. Yeah, it would be cool if you shared a database and just kept adding on to it. That would be fun. And you can put files under /temp, and you can make them like readable, writable to whoever, if you want to do that. Just remember that if somebody like clobbers the file, it'll be clobbered, so you might want to make copies. But yeah, that would be fun. So here's 20Q big, right? And it's got a number of questions up front, and then we start getting some answers, and then some more questions and answers, and so on. And you know, this does not go with that question, right? So this is a nightmare to try to understand for you and I, but really easy for the computer to understand. So let's talk about output first. So suppose this is what your tree looks like. So let me find a tree like this. Okay. Is it an animal? Yes. Is it furry? Cat, turtle? No. Laptop, rock. All right. So to write this to a file, just write in node left right order. Okay. So do a pre-order traversal. Got to do it like that. If you do in order, post order, doesn't work. So first thing we write out is question, is it an animal? And then we go down here and we do node left right. So question, is it furry? And then we come down here and we do node left right. So that's an answer, is a cat, and there's nothing to the left or the right. So we visited this, we did the node, we did the left, now we're going to do the right. There's an answer, turtle. And now we've done this node, we did the left subtree, we're going to visit this tree in node left right order. So that's a question, is it electric? And then we travel to the left, and there's an answer, laptop, and there's an answer, rock. Ran out of memory there. So node left right traversal, right? We know how to do that. So recursive algorithm. We did an in order traversal in the sample code earlier this week. Same idea. Just print the root node's data first. And you know, if you've got a flag in your memory structure, how do you print a node? Well, look at your flag. If it's a question, print a Q. If it's an answer, print an A. And I think these have colons on them. And then, you know, print the data value. And then call your recursive NLR on the left subtree if the left subtree is not null. Yeah, I saw Smurfs in there. All right, so outputting your tree to a file is pretty straightforward. Just NLR traversal. Slightly trickier is ingesting the file. Oh, we've only got 1 second left. Oh, we're out of time. All right, so we'll talk about ingesting on Monday, but like I say, you can cobble together a tree in memory by hand, and work on playing the game and work on updating the tree and writing it out to the file. Ingesting basically read a line, right? Make that a node, and then if it's an answer, it's going to be a leaf node. If it's not an answer, you're basically going to read that in, make a node, and then recursively ingest from this point down whatever you get. That becomes your left child. And then wherever you left off, read in from that point in the file, using your ingest function, take the tree that comes back, make that your right child. Yeah, that did fly by quickly today. And if we get to this in the afternoon section, there'll be video on that. If not, we'll get to it Monday. But we got a couple of weeks for this, so getting the basic gameplay running and updating your tree, that should keep you busy over the weekend. All right, we are out of time, so have a great weekend, and I will see you on Monday.